Welcome to ECE1786, Creative Applications of Natural Language Processing. My name is Jonathan Rose, and I'm the instructor in this course. I'm releasing this video early for two reasons. First of all, I want to tell you exactly what this course is about and what it's not about, so that you can make an informed decision as to whether you really want to be registered in this course. But secondly, and quite importantly, in order to take this course, you would need to have a background in machine learning and in the software application of machine learning. And so I'm going to talk about that because it's really important that you know that and to understand that I will be requiring you to tell me your background in order to see if you can stay in this course. But let's get started. Our tradition at the University of Toronto is always to acknowledge the land that we sit on. Toronto itself is a city of immigrants, and my parents came here to Toronto in 1952, and it's pretty likely that you or your parents are very new to this country because that's the nature of Canada. This is not a new feature of Toronto, though, or Ontario or Canada. For over 15,000 years, Toronto has been a gathering site for humans, including the Huron, Wendat, and Pedon First Nations, the Seneca, and most recently the Mississaugas of the Credit River. Today, Toronto is still a meeting place for Indigenous people from across Turtle Island, which is what they call North America, and immigrants, both new and old, from across the world. I am grateful to have the opportunity to work with you in this community and on this territory. So welcome to ECE 1786. This course is about methods for automatic understanding and generation of human language. I find this field very powerful because language is the pathway in and out of our human brains, and getting a connection to computers through that core pathway is an incredible capability. Until recently, it was very difficult for computers to talk to humans using language, and we'll talk about why that's so, and cover the inventions that have made sophisticated communication between humans and computers possible and led to other remarkable capabilities. And some of those capabilities may one day include, I believe, in your lifetime, that you'll be able to get decent medical care talking to a computer. Someday you're going to walk up to a computer when you're not feeling good and you're going to say, I don't feel good. And the computer's going to say, well, what's the matter? And you'll tell it, and it will do a better than human job of talking you through or analyzing what the problem is. Because once we get it right, we'll be able to make lots of copies of it. So I think that's going to happen in your lifetime. And I think you'll be able to get mental health talk therapy anytime, anywhere from a computer. And in fact, it's this last thing that is my current research focus, and it's the reason I'm here teaching this course. My current main research project is automatic talk therapy from a computer to help someone with smoking addiction. We want to help people do something actually quite specific. We want to help smokers move towards the decision to quit smoking. And we're trying to make that possible by using a known clinical method and modern natural language processing approaches to take them there. So let me show you just to give you a sense of why I'm excited by this area. Here's a little tiny snippet of a current conversation that we are having with smokers, actually, that our system is having with smokers. And the process always begins with various kinds of open-ended questions that are scripted. So nothing special. We wrote this question, and this is in the middle of the conversation. So we say, what will it look like when you have made this change that has already been talked about in your smoking habit? And this is a real user, a real smoker, said, I will feel good about my accomplishment, feel health improvements, and will be able to save money. This statement is what our bot said. And it said, oh, you think that by making this change, you will be healthier and be able to save more money, which, if you look at it, is kind of a restatement of what the user said. But what is interesting about that second statement is that no one in the research program wrote that. It was generated by a neural network language model that was trained to, well, one of the things it was trained to do was to simply restate what was said to allow the person to keep talking. And so This used to be very, very hard to do, and this is quite remarkable that we are getting pretty good at doing this and a bunch more sophisticated things. Here's another example where we ask the question, the same question, what will it look like? And the person said, I wonder if I could do it because I'm an addict. And the bot said, the trained bot said, you are concerned that you would be unable to stop if you tried. So again, we didn't write that, but the language model that we're using understood what addict meant and rewrote it this way. And to my mind, that's actually quite a remarkable thing. That's what we're up to in my research. And it's, why I'm here in front of you is this project actually is kind of the cause of it. But in that work, as I've learned more and more about what language models are capable of, I keep getting amazed. And the most amazing thing that's come along, one of the most amazing things, is a model known as GPT-3. And you can go play with this thing at this web address. And it's very easy to do these days. You get a little playground like this, and you can do, it is quite remarkable. Quite remarkable what's possible. And here's what you can do. You can do, this has got a name. This is called zero-shot learning, where you just tell the model what you want it to do. And I told it, with some advice from from OpenAI, write a creative advertisement for the following product to run on Google, like a Google advertisement, aimed at ice hockey players. And why is it aimed at ice hockey players? I'm an ice hockey player. I made up this product. It's an automatic alarm to alert hockey players that they are about to crash into the boards. It's just a silly thing, a silly idea that somebody would have some kind of product that would alert you if you were falling too close to the hockey boards. And here's the output. The model wrote an ad that sounds like your typical goofy ad. Introducing the board checker. This innovative new product will help keep hockey players safe on the ice by automatically alerting them when they're about to crash into the boards. With its easy-to-use design, the board checker is a must-have for any serious hockey player. So what's remarkable about this is that we asked it to do what we wanted it to do in English with a little bit of information, and it did it. And every time you run this, actually, as you'll learn in this course, you often get a different answer. And actually, the first time I tried this, the answer I got I liked even better. And here's what that was. It has a sort of cheeky feel to it. It says, looking to avoid those costly and painful collisions with the boards? Look no further than the Board Be Gone automatic alarm. This handy little device attaches to your hockey stick and uses sensors to detect when you're about to crash into the boards, and so on. It just sort of, the language model made up stuff that sort of makes sense, and this and many other things are remarkable and new things. If you go to the GPT-3 Playground from OpenAI, and you look up in one section, it'll take you to this set of examples of all kinds of different things that it can do, and this is just the surface of what's possible, including automated programming, summarization, arithmetic. The list goes on, and it is truly surprising what knowledge has come about, what automation of knowledge has come about because of these language models. And the big news in the past 3 or 4 months is this model called DALL-E 2 and its competitors, which can take words and produce pictures. And so DALL-E 2, I pulled this off of the Reddit, the subreddit that's talking about this, where people post their favorite things that have been produced by DALL-E 2. This is someone asked the model to create a picture of a close-up wide-angle photo of a cat wearing sunglasses. And so this is not a real picture. This is just created from the model, and there's something remarkable going on here too. The thing that makes language difficult and language processing difficult, or made it difficult, was the ambiguity of language. The fact that words have multiple meanings. Tank can mean a military piece of hardware, or it can be a thing that holds fish, or it can be a verb. Bank can be a place to hold your money, or it can be the bank of a river. A duck could be an animal, or it could be a verb. And so you need the context to figure out what these words mean, and that sort of makes it tough. It made it tough for computers to figure things out. And we humans can kind of figure out the ambiguities in statements like this, like milk drinkers are turning to powder is talking about milk drinkers choosing powder rather than liquid milk, as opposed to the drinkers themselves becoming powder. And if you read these sentences, you'll realize they look kind of ambiguous, but you could figure out what makes sense, including I saw bats. So that ambiguity has been at the core of the difficulty. But the ambiguity is now much easier to deal with using neural net-based approaches to natural language processing. Since the deep learning revolution began in 2012, right here at U of T, actually, our university gets credit for launching the modern era of successful artificial intelligence. Right around that time, a key step, building on some prior work, of course, but a key step in word embeddings, which we're going to cover, occurred right then. And then sometime around 2018, the transformer architecture proposed by Vaswani et al. Launched the modern renaissance in natural language processing. And all these models you might have heard of are things we're going to cover in depth. So I'm trying to get to the root of what's going on in these models and how they do what they do as best we can understand, because there's a lot of mystery still, is the subject of this course. That success has enabled fantastic translation, much better than ever before, the ability to classify language, and we'll be covering that, and to create dialogue, the thing that I care about in a therapeutic context, but it has many other applications as well. So that's what the course is covering. I want to spend a moment talking about two other courses that to relate this course to two other graduate courses that you may be considering. As I say, this course is focused on neural network approaches to natural language processing. This is a 60-year-old field, which previously used predominantly a procedural methodology based on a human understanding of language. For example, and this kind of way to think of NLP is referred to as computational linguistics, where you think about the grammar, and this shows up in a task known as parts of speech tagging, where you figure out if each word is a noun or a verb or an adjective, and all the different kinds of things that words can be, and explicitly parsing language to interpret it. And so that's computational linguistics. And CSC2501, that's the graduate course, but it's a cross-listed undergraduate course in computer science, is called Computational Linguistics, and it's taught primarily by Professor Gerald Penn. And so that course is largely computational linguistics with a smattering of neural-based approaches, because they are remarkable. We will make some, but very limited use of the computational linguistic approach, because it's being pushed aside largely, but not completely, in the neural approach. So that's what's different between this course and that course. A more closely related course in computer science is CSC 2501, also cross-listed undergraduate CSC 401, Natural Language Computing, principally taught by Professor Frank Rudix, and you can look at these courses there. CSC 2501 has a much broader coverage of topics surrounding language. And so in a sense, it's a superset of this course, and it includes things that I do not cover, such as Markov models, entropy, automatic speech recognition, information retrieval, and in fact has a little focus on dialogue itself. Now, so that course is much broader, but as a result, not as deep as this course. We will focus much more narrowly on word embeddings, deep learning, this notion of statistical language models, which is at the root of all this, and transformers. And so much less breadth, more depth, and I will be taking more of an engineering software-based focus. That is, we'll talk about software, that you need to have software skills in order to do these things. It's not tangential to getting things done, which is what engineers do. So that's what I'd call a more engineering focus. The core learning outcomes of this course are understanding these things, what a word embedding is. It's at the root of everything, and we'll spend the first assignment on that, actually. And then we'll use those word embeddings in classification tasks as a way to kind of get entry into a key thing we do with in this form of NLP. A big focus of the course will be about transformer models, which is the thing that brought all those kind of amazing things that I showed you before. I'm going to try to teach it in a way that I don't see it being taught, actually, from its global structure, understanding what is believed to be going on in those models, and then how those global structures interact, how it's trained, and then in the detailed substructures, like things, a very important thing called attention, the transformer stack, and a whole, in my view, controversial look at the encoder-decoder structure of these transformers. We'll use them to classify, and then also use them to generate language, which is what you saw that GPT-3 thing doing. We'll be using PyTorch and a really important website / software archive / model hub called Hugging Face. And we'll be diving into the software implementations of these things in a way that build knowledge for you from the small to the big. We will try to cover some of the limitations and biases of language models. It's something that always has to be addressed in all AI neural network courses, I think, because, for reasons we'll discuss. And maybe it's one small item, but it's actually worth most of the grades in this course. There will be an open-ended project that you will do in groups. And to my understanding of how to teach engineers, you always make them do a project because that's what engineering is, and it's what research is too, actually. Okay, so I'm really excited to teach this course, and I hope that you stay in it and participate with me. It's going to be a journey of discovery because, as I say, this is a brand new course, and it's the first time it's been taught. However, there are prerequisites, and one reason I'm harping on this is we don't stop you from registering this course by first checking your prerequisites, so I have to do that now. And it is absolutely clear to me that there's a whole another course that needs to have been taken somewhere that allows you to take this course, and it's on machine learning. So this shouldn't be a surprise. I know that because the course was new, when you first maybe registered in this course, the only thing on the website was the title and these prerequisites, but the prerequisites were there. This is now there, which is kind of a rough description of what we're going to teach in this course. And so let me elaborate on what this means, what these prerequisites mean. And so fundamentally, this course does not introduce modern machine learning. And that means you must have a background from a course in machine learning that has depth in neural networks and all the things associated with it, and how to do a bunch of things that I'm about to describe. And the reason you must have this is because you'll just be lost for the assignments, because the assignments assume that you have that background, and that's a lot of background. The acceptable University of Toronto undergraduate courses, any one of these is good enough to form as a basis for this course. So there's a couple different forms of this course, ECE324. I actually taught this one, Introduction to Machine Intelligence. It's now called Software and Neural Networks. Introduction to Machine Learning, ECE421, is also sufficient. APS 360, which is in the AI minor in engineering, is actually built off of this course, actually, and it's fine too. And in the computer science side, these course numbers have changed some, but the current course numbers that are relevant are these two. So those are undergraduate courses. Another course that's acceptable is the ECE graduate course, Introduction to Machine Learning. It is the graduate equivalent of ECE 421. So if you've taken those courses, this course is okay. If you didn't go to U of T for your undergrad, and that's most of you, you must have taken a course that's equivalent to one of these. And I'm going to be asking to know what that is and learn about that course. The next few slides will describe that necessary background in detail. In order for me to know this, you will find, if you're registered in the course, a survey on Quarkus. I'll show you where that is, which you will answer a bunch of questions that allow me to determine if you meet the prerequisites. And you should listen to this carefully and read those questions carefully and ask yourself if you're comfortable in those areas. If not, take one of those courses, come back next year and take this course. So what do you need to know already? Well, you need to know machine learning. You need to know what classification is versus regression. So a logistic regression system does one of those two things, and a linear regression system does the other thing, and you should know which is which. You should know what binary classification is versus multi-class classification, what supervised versus unsupervised learning is. And you should know what data labeling is how data is labeled. You should know basic knowledge about neural networks and how they're trained. So what is a linear neuron? What are its weights and biases? What is the nonlinear activation function used in a basic neural net, such as sigmoid or ReLU or tanh or other things like that? You should know what a multi-layer perceptron is. We use them everywhere. What is a loss function? An objective function. What such as binary cross-entropy or multinomial cross-entropy. Why are those useful and important loss functions? What is a loss function? What is the softmax function and why do we use it? These are all things that you need to know to start this course. Why do we have training, validation, and test sets? Why do we have 3 separate test sets, and what is their purpose? And what is a training and validation curve? It is something that shows you what's happening during training and teaches you all kinds of things. You're going to have to show those things and talk about them in the first assignment in this course. What is gradient descent? And what is stochastic gradient descent? And why is it super important, actually? What is hyperparameter tuning? What is regularization? Things like batch normalization, dropout, and weight decay. All basic things that are kind of the initial things you need to know in order to get going in this course. In more advanced neural networks, you need to have been exposed to a convolutional neural network for computer vision, a CNN. You should know what kernels are and batch normalization. You should have some understanding what a recurrent neural network is, an RNN. And it's kind of interesting, one of the most important things to know that makes this field useful is something called transfer learning, that you could take a network that someone else trained at the cost of thousands or hundreds of thousands or millions of dollars and just repurpose it for something new. And that's actually one of the most important things that happens in this field, and we'll be making big use of that. And that repurposing is called fine-tuning. You also need to know how to build all of those things using a software framework. So you must have had experience in TensorFlow or PyTorch. Those are the 2 main frameworks that people use. And I believe if you know one, you can figure out the other. So I don't care which one you know. We'll be using PyTorch, actually. This, of course, implies a lot, that you have enough experience in Python to be useful. There's lots of levels of Python, but you need to know how to use Python in a reasonably effective way, or else the course may become overwhelming right away. You should have written full training and testing loops with applications with significant data sizes. You're familiar with what tensors are. You've struggled through the notion of shape and how the shape of a tensor, figuring out the shapes, and all your bugs show up when you mess up the shapes or the dimensions of tensors. You should be familiar with the NumPy framework because it's always an adjunct to these systems. You should have some idea of how to debug a neural network, which is a skill all by itself. So these are crucial things to really be able to get going. There are some data science concepts that underpin most of the work that we would do. Ideas like false positives, false negatives, true positives, true negatives, which lead to specificity and sensitivity or recall and those sorts of things. You should have some sense, although we can quickly teach the area under the ROC curve, the receiver operating characteristic curve, and you should know what a confusion matrix is. So those things should all make sense to you for you to take this course. I need you to tell me which of those things you have so that I can look at that and make a judgment as to whether you can stay in the course. That's how I'm going to enforce the prerequisites. So if you're registered in this course, go to the Quarkus website and look on the left-hand side and you'll see a thing called quizzes, and I'll have posted there, it's not here actually, but I'll have posted there a quiz that's not graded. It's just the thing that allows you to stay in the course. And so you must answer this or you can't stay in the course, and you must give evidence that you have this prerequisite knowledge. I'm sorry to harp on this, but I've designed the course based on that, so it doesn't seem unreasonable to ask you to have those prerequisites. Okay, now what I'd like to do is spend a moment telling you a little bit about my teaching philosophy, because that informs the design of this course, and explains why the particular elements are in the course I've created. The first element of my teaching philosophy is to teach fewer things, but to cover those things more in depth, and to try to explain the intuition behind each approach that we're talking about, so that you understand things in greater depth. So other courses might go broader and narrower. I prefer to go deeper and narrow rather than broader. And once you've learned sort of the core in a field, I think that enables you to learn more on your own. The second key philosophy is your learning doesn't actually come from my lectures. Some of it does, some sort of basis for it does, but to really truly learn something, you have to work with it and build it. And so in this course, that means writing software and then experimenting with that software, and then answering questions and contemplating what those experiments teach you by watching how these algorithms work. Particularly neural networks need this, because this is an experimental discipline far more than a theoretical one where you set out to make an algorithm do something and it does it. That's not how neural networks work. And my third deep philosophy in teaching is, if at all possible, students should create or build, in the engineering sense, open-ended projects. Because an engineer is someone who can navigate a fuzzy idea, make it more concrete, make sure it is the thing that's needed, and then to navigate what's needed to do to create it. And so that involves both motivating it and then figuring out how to make it happen, and then also describing it well, because we must, as engineers, learn to communicate with other people. And so this course will have a fair bit of communication component in it, and hopefully you'll get feedback and get better at that part too. So that's the underlying philosophy. Let me tell you about the course structure and kind of the grading. So here's what you're going to be asked to do. There's going to be 4 assignments worth a total of 40% each. 10% each, a total of 40%. And then the project is going to be worth a total of 60%, broken up into these pieces. So the proposal will be worth 10%, and there's both a document and a presentation involved there. There'll be an interim report. There'll be an in-class final presentation, and there will be a final report. In addition to that, something that I think is going to broaden your learning is you'll be asked to do peer reviews of your peers' work in the project. And so we'll talk more about that in a moment, and that's worth a fraction of your grade. The 4 assignments look roughly like this. These are the dates when they're going to come out. This is when they're going to be due. They're tentative dates because I'm still building this course. We'll begin by talking about word embeddings and their properties, their meaning, and how to train them, and move on to classification using word embeddings, and then dive into transformers, understanding the code for them, training them, fine-tuning them, and then using the big ones. And finally, the last assignment is generating answers to questions using transformers. So switching over to the generation side of transformers. The peer review that I'll ask you to do is that each individual student will be assigned a specific another group project to give feedback to, both on their proposal, presentation, and document, and on their interim report. And you'll be asked to produce specific and useful feedback for that group, and you'll be graded on the quality of your feedback. And so, it's a thing I think is worth doing. So, why is that doing that? The textbook in this course is free. Professor Dan Jurasky and James Martin from Stanford have this great book, the 3rd edition of which is being drafted as we speak, and it's in reasonable shape, and it has a good basis for what I'm going to teach in this course. It's called Speech and Language Processing, and it's free. You go to this link, and you get a PDF. It has one issue that it doesn't have a chapter 1, and currently they say, well, the chapter 1 of the 2nd edition will suffice for now, although it is a little out of date. but that's also free. So you can go get the second edition as well. Sorry. So the textbook is free. And you're going to need to run software. You're going to need to run software on a fairly decent computer in this course. And fortunately, Google has put forth something that I'm sure you're familiar with if you've got any background in this. Google Colab provides you with not only free computation, it will let you use a fairly low-end GPU to accelerate your software. My suggestion is that you pay a little bit more, since there's no textbook cost here. I think it might be okay. But it's optional to get access to Google Colab Pro, which is I think $14 a month, and it will allow you to have access to better computing facilities. There's an even more expensive one called Google Colab Pro Plus, but I'm not suggesting that. So. Okay, let's talk more about the project, because that's 60% of the course, and as I said in my philosophy, it's something I really believe in. The project will be done in groups of 2, at least that's what I'm certain of now. It does really depend on how large the class truly ends up being. And at this point, you should not think of doing a project by yourself in a group of 1 or a group of 3. You have to find a partner to work with. The topic will be of your own choosing with some constraints, but I will be the one to approve it. So you'll be asked to give a rough declaration of what it is, and I will offer feedback and approve or not the topic. It, of course, must relate to natural language processing and the material covered in this course. I believe it should be an application of natural language processing. We'll use what we're doing and apply it somewhere. Some of you may wish to do a research project on NLP itself, and I reserve the right especially to approve that or disapprove it. In my experience in doing this kind of thing in the past, that has run into all kinds of trouble. So an application is how you should be thinking. And one final constraint I want to flag now, and we'll give more detail on this. In my experience in teaching machine learning courses, one of the most important things that cannot be ignored is the collection and labeling of data. And so what I will not allow is for you to simply go and get a data set someone else collected and cleaned and labeled and chew away on it to see if you can get better results, because that's a kind of classic thing to do. Your project must include some amount of collection and labeling of your own data, because I believe the engineering of that is actually a really important thing. Now, this is a tricky requirement because you could easily spend all of the time available to you collecting and labeling data. So it will have to be a discussion. I have successfully imposed this on in a previous machine learning course, and I think it's important because without it, it means you're missing, what some people argue is, 70% of the work in the machine learning world. The project stages look something like this. You have to find a partner by the end of October. You need approval in principle of your project. That's where I approve it by October 24th. You'll need to submit a written document and present it sometime around October 31st. Actually, right near then, we'll have an extra lecture to fit in the extra proposal presentations. They're just 5-minute presentations. An interim report will be due November 21st, and then final presentations will happen in the week of December 6th, and we may need an extra lecture there to do that as well. And then a final report will be due on the 7th, the last day of classes. Since I'm still building this course, all of these dates are tentative, so we'll confirm them later. You probably want to know a little bit about who's going to be teaching. Let me tell you about myself and the TAs. I've been a professor in electrical and computer engineering since 1989. I did all 3 of my degrees here at U of T, but I did a postdoc for almost 3 years at Stanford University. My research, as I mentioned earlier in this presentation, is in the automation of medicine and mental health, and I'm focusing on really using natural language processing, it's the pathway in and out of the brain, to help in mental health diagnosis and therapy. And most recently focusing on conversational systems for mental health. Previously, I had a whole other career in a whole other area in the field of field programmable gate arrays, FPGAs, which you may be familiar with those. In fact, I have a bunch of entrepreneurial and business experience as the co-founder of a company that worked in that field that was acquired by Altera, a big FPGA vendor, back in 2000. And I worked for that company for 3 years as a software engineering director. That company is now was subsequently bought by Intel. I've also been the chair of the ECE department for 5 years, back about a decade ago, and I currently chair the Engineering Entrepreneurship Hatchery Advisory Board. I oversee the incubator that is here in engineering, and I am very keen on entrepreneurship, and so happy to have conversations about that if you're doing such a thing, if you're interested in doing such a thing. I have all kinds of fellows to my name that I acquired, fellowships that I acquired in my previous field, to be clear, not in the current field. And I'm also a senior fellow at Massey College, which is a place that does what this course kind of thinks about doing, which is to bring together multiple disciplines. One of the teaching assistants is Zining Zhu. He is a PhD candidate in computer science, and his thesis revolves around methods and applications for probing deep language models. And he's actually worked with me before in another course. And the second TA that we have so far is Andrew Brown. He's a MASC candidate that I supervise, and his thesis is around that smoking cessation chatbot. Zining Zhu is supervised by Frank Rudix over in computer science. There are two main course websites. The Quarkus website, which you would have access to if you have been registered in the course, and which you don't have access to if you're on the wait list. That's where the assignments will be released and submitted. You'll see your grades, and announcements will come through that pathway, so pay attention to those. We will use a separate Piazza website for a discussion board, and you will see on Quarkus an announcement that tells you how to access that board. If you don't have access to it and want it, just email me and I will give you access. So that is everything I wanted to say in Lecture 0. Remember, the message is you got to check and make sure you have the prerequisites, and you have to fill out that Quarkus survey in order to stay in the course. If you have questions, post them to that Piazza discussion board or bring them to the first lecture, which is Tuesday, September 13th, from 10 a.m. to 12 noon in the Galbraith building, room GB221, which looks exactly like this. I look forward to meeting you then.